Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheCS. Today, it is my great pleasure to introduce to you Dr. Mark Nasila. Mark is the Chief Data and Analytics Officer at FirstRand Risk. He's also a member of the faculty of the Singularity University, and most importantly, he's also a member of the steering committee of NITheCS. Yeah, so thank you very much, Mark, for joining the NITheCS team. Thank you very much. So Mark is, of course, working in the field of artificial intelligence and machine learning, and he's responsible for the adoption of these famous fourth industrial revolution tools at FNB, making it one of the most progressive banks that we have in South Africa. He's also a very requested speaker at national and international conferences, and he's published a lot, and some of you might have read some of his articles in the Business Day, the Mail and Guardian, the Daily Maverick, and many others. Yeah. By training, Mark has a PhD in mathematical statistics from the Nelson Mandela University, and he took part in the executive program of the Singularity University in South Africa. Yeah? Recently, he was also named one of the top 100 innovators in data and analytics in a global program called Corinium Global Intelligence Survey. Yeah. So Mark, we are really very happy to have you with us today. And maybe while you start sharing your screen, I quickly introduce the other people that the participants see on the panel. Yeah, with us this evening is Amira Abbas. Amira is a PhD student in my group, and before joining us, she was a competitor of Mark, because she was doing essentially the same job of Mark for another bank. Yeah, and since Amira knows Mark since many years, I asked Amira to join us and help us moderate the question. Ilya, most of you have seen Professor Sinaisky. He's also based with me at UKZN, and he's always kindly agrees to be the co-host for the event. Okay, Mark, we can see your slides. You're most than welcome to start your presentations, and please, participants, make use of the Q&A facility to ask your questions, and Amira will keep an eye on them. So thank you very much, Mark. You're welcome to start with your presentation.
Thank you so much, Francesco, for that wonderful introduction, and to NITheCS, as well as to all the participants who are joining us on this Monday afternoon. I hope you're all keeping warm and safe. Also, thanks to Amira and Ilya for being a part of the co-hosting. So today, I want to talk to you about the concept of design thinking. And while design thinking is a concept that has been there for a long time, especially in the likes of fashion and other types of industries, we are seeing that at a time where every single organization, whether it's a public sector or a normal corporate organization, is investing a lot in technology and data, centered around capabilities such as artificial intelligence and machine learning, it's becoming more and more critical to start thinking about increasing the likelihood of succeeding. Every single organization wants to meet the digital expectation. Every single organization wants to be more efficient. Every single organization, whether it's a country, jurisdiction, is investing in these capabilities to making sure it keeps up with emerging risks. And not just because the whole world is changing based on globalization, which is enabled by the same technologies, But also we're going through a time where some of the social challenges we're facing require us to be more disruptive. They require us to guarantee that we're going to succeed with our investments in these areas. And as Francesco said, as part of my role within First Run Group, and specifically the risk area, it's not to just envisage the future around leveraging AI and convince my stakeholders to invest in these things. The differentiator is these capabilities working in real life. And I want to straight away point your attention to one of the key measures that is coming up from recent studies showing that there is a group of organizations driven by design thinking that is actually doing much better than the rest of the organizations. So design thinking is a measure which was developed by Motive and is traditionally focused, is traditionally centered around organizations that are design thinking driven or design driven. And when you look at the graph you're seeing here, you've got a group of organizations like Apple, Coca-Cola, that are driven by design thinking strategies. And the studies have shown that these organizations are exponentially growing at a faster rate compared to the traditional S&P companies. And at a time where data and technologies are at the center of almost every form of innovation or reimagination of the process, you can understand that the way organizations use data, creativity around data contributes to them being successful more than the others. 2 days ago, I just checked the recent value. That margin of difference or value or growth over time has just increased to 280%. And therefore, organizations have to think beyond just investing or developing technical competencies. And it's something which I will touch on. So my main objective in this talk is to give you or build on a background while touching on AI and machine learning applications that have failed, especially due design related issues, and use that to build on the formal definition of design thinking. I will also touch a bit on the design thinking process. I'll touch on a few use cases or scenarios in AI and machine learning applications that require us to apply design thinking. I'll also talk a bit about the design thinking process, or when it actually becomes nonlinear, and how design thinking incorporates the role of machine learning or AI when you're reimagining processes, especially re-engineering processes and more for business applications. And then I'll finish the conversation. Where is the intersection between design thinking and data science, or where is the intersection between design thinking and digital transformation? And therefore, I'm hoping by at the end of this agenda that you all appreciate the role of design thinking. You also appreciate that design thinking can elevate the chances of success, but also design thinking will be at the center of helping us to actually solve some of the challenges using data and these AI-related capabilities. So, what is design thinking? To set the scene up, I just want to point your attention again to some of the investments that have gone into the field of AI. And the numbers you see there have just been recently published. The finance sector, by the end of this year, will have invested 12 billion. The public sector have invested 8.9 billion. The message behind this slide is that every single organization knows that for it to modernize and become better, they're putting in a lot of money here to try and set themselves up for the future. Just in the banking sector, McKinsey recently estimated there's almost 1 trillion worth of value if done properly. And the key word is if, with more of the opportunities in the marketing and sales, as well as leveraging AI and machine learning to reimagining the risk processes, with a few applications in finance and human resources. But in general, across all industry, we're looking at almost $16 trillion worth of value that is available if these capabilities are executed correctly. Already in the banking space, over 80% of the banking sector is aware fully that AI and machine learning will create an advantage with with billions expected to come from automation of processes and efficiencies, which will result into cost savings. So you would think that if people already are investing because they already know where the advantages are going to come from, or the role of AI in reimagining their areas, you'll think it's actually given that chances of succeeding are quite higher. But I also want to paint a different picture, and these are, you can see these are numbers that have recently been published. Gartner has told us that 85% of projects are failing in the data sphere. Up to 87% of projects don't even make it to production. So then the value or the opportunities I just showed you, you can imagine how much of that opportunity will fall away. Only 20% of organizations deliver value. But if you look at the bottom figure, which is actually so alarming when we're talking about AI, which is actually critical in solving some of the complex problems, only 14% of organizations have reported to have deployed AI capabilities or use cases in production. So, and this is not considering out of that 14%, there's a very big chance that a lot of them are actually not successful. So investment is not just the only issue. I do know some organizations and some areas are struggling with investment, but we're talking about challenges where there is critical investment. I want to touch on a few use cases or a few areas where we've seen failure or things go wrong, even when there was so much competencies. And I want to start with a very famous, use case of, Wozniacki, where him and his wife applied for credit facility. These credit cards were designed by Goldman's, and his wife received a very high interest rate than him. And he was very adamant that there was issues in the way these algorithms were designed, because how come someone would come from the same household, you live the same lifestyle, the same portfolio, yet one of the partners get a very, very high interest rate or even a different limit. So think about it from a design perspective. Here's another use case, and I think this also made a lot of noise in the media, where Target uses a lot of behavioral data to make predictions around lifestyle so that they can recommend products to you. And in this case, the father, the girl's father used her phone, and the marketing was done through the phone. And that's how her father found out that the daughter was pregnant, when the product recommendation was sent to this phone. So what you need to think about here, while Target made correct predictions based on the girl's behavior around shopping, was it very ethical, or could they have done it in a different way to make sure that this is not, this situation doesn't result from that whole scenario. One of my favorite, or two of my favorite use cases was by Leo Breman. You all know Leo, some of the work he's done around, random forests. But I picked these two use cases from his paper, which he published around statistical modeling, the two cultures. And the first one was what he called the Ozone Project, where the government asked him to help develop algorithms or use data to predict when they're likely to have ozone. And ozone is basically a very smelly gas that results when there's a reaction, a radiant reaction between the sun and some of the debris or stuff from the factories. And it was important for that prediction to be there so that the government can advise people on how and when to commute to work, because the ozone is a very dangerous gas, can even lead to people having respiratory infections or even cancer. Now, he could do this comfortably within 3 hours, but 3 hours was too late, because within 3 hours in the morning, people had already started going to work. When they asked him to try and make these predictions at least 12 hours before, he had too many false positives. And I'm sure all of you have use cases where you've had so many false positives. In that article, he talks about, some of those algorithms that were existed in the early 80s were a bit primitive to be able to generalize the ozone problem much, much better. But a different use case, which he actually solved successfully, was the chlorine project, where he was required by the Environmental Policy Agency to predict or to analyze mass spectrum and detect whether there was the presence of chlorine, because much of the work the Environmental Policy Agency did was to ascertain whether some of the substances had toxic, or some of the mass spectra had toxic substances. When he started the project with a lot of data, and he started by looking at linear discriminant approaches as well as quadratic approaches. And he found it very difficult to solve this problem until when he considered decision trees, which gave him an over 95% accuracy. This and other problems he solved led him to make a couple of conclusions. That one is that you've got two cultures, which that's why he called the article the two cultures. Those who approach problems and make assumptions about the data, and those who approach the problem without assumptions and focus on finding the best algorithm to solve the problem. And where he failed, he felt that he had made wrong assumptions about the stochastic distribution of the data, which he considered is considered and probably a way which he would have approached the problems as part of designing these solutions. Facebook, this is another famous case where there was a 70% failure rate in chatbots responding to customers. And the key issue here is that trust was put on these chatbots without ascertaining how much the algorithms understood the conversations. There was not enough testing done, and instead of just letting these algorithms being up there, the studies show that they should have only allowed the chatbots to comfortably drive 30% of the conversations, other than have all these algorithms there. So Night Capital is another very exciting use case, and it's not exciting because it's a trading use case, but it is exciting because it was a use case with so much potential, but went so wrong because of wrong design implications. Knight Capital was one of the largest equity traders in the US. And when I say largest, they were trading about 3.3 billion trades a day, worth over 21 billion US dollars. Because of these high frequency trades, they decided, I think we need to have an AI system that would take over some tasks from human beings. And you know very well the fundamentals of trading. A seller posts an asking price and a buyer decides, okay, I think I'm going to offer something less. And if the seller is happy with it, then the transaction will take place. But they didn't test this algorithm properly, and it did exactly the opposite. And in the space of 45 minutes, Knight Capital lost over $450 million. So literally in every single minute, they were losing over $1 million because they were buying stocks at a higher price other than at the asking price, other than buying it at, you know, at the selling price, which has been agreed by the buyer and the seller. So there's also a lot of lessons to be learned in that area. Another example, as I finish, some of the use cases have gone wrong. The Autopilot systems have been in existence since 1914, but we've seen instances where things have gone wrong, including the recent 737, where you know, an autopilot went wrong. But this specific one was a flight that was on its way to Norway. It's a cargo flight, and the pilots got a wrong indication from the sensor of the plane, where the pilots were trained to follow instructions. Whatever is displayed to you, you have to follow and go by with it. But in this particular case, the sensors on the gyro of the nose of the plane got wrong data, one of the sensors, and it indicated to the pilots that no, there was a mistake or there's a failure and the nose of the plane was facing up, when it was not. So the pilots had to act on that because they were trained to only depend on that system. And they decided to try move the plane downwards, not knowing that actually they were actually crashing the plane. And this is also an example of, where a design of a system went so wrong, where the human and machine partnership in the algorithm was not catered for properly, so that there was so much dependence on what the machine told the person controlling the system. And when things go wrong in that situation, you realize that probably someone should have thought about it in a different way. Because of time, I just want to rush through these two examples. AI tools, when COVID started, everyone rushed to come up with AI tools to catch COVID. Douglas from MIT came to the conclusion that, while a lot of people build these algorithms, they rushed into them while looking at data that was not sufficient enough to be able to generalize properly. So there was so much misdiagnosis, false positives, false negatives. Some doctors were getting infected because they were getting too comfortable from AI tools that were giving them false comfort. I think you've all heard about this use case where, a beauty AI system was so biased, out of 44 winners, only one of the winners was a person of color. Microsoft and NVIDIA eventually determined that, they used very, very wrong data. I won't touch on this and this, but when you look at a summary of these use cases, some of them are because of biased data sets. Some of them are because of misuse of algorithms, interference of algorithms. The one I've just skipped here is where someone interfered with an algorithm, and the book that was actually valued at $45 ended up being listed for $23 million because someone interfered with the algorithm, and this is almost a control monitoring process that should have been set up to make sure that any adjustment on the algorithm is monitored and evaluated properly. All these have one thing in common. It's a design-related issue. And for cases where there are biases, you could say, oh no, we do have, there's certain controls that should be put in place, including things like, having diverse teams. But a lack of diverse teams, for example, is also it's a design issue, because when you put a team together, you should envisage what is expected in the future of the outcome. So think about all these failures. If you're investing in technology and AI and you've got more failures like that than successes, you're likely to fall in the wrong end of this gap. And therefore, we have to develop a mindset around creativity that minimizes these mistakes, but also ensures that we're solving problems. And this brings me now to formally defining what is design thinking, and more even design thinking in relation to AI and machine learning. So I've put two definitions here. Apologies about there's so much text. This one is from the Interaction Design Foundation, where it says, it's a way of thinking, a way of working, as well as looking at hands-on methods. It revolves around the deep interest around the people for whom we're designing the products or services for. Essentially, it's a problem-solving approach around the holistic or the customer-centric perspective of the people who we're designing the solutions for. The next definition is actually very, very similar. And you realize that the design thinking is a mindset. It's a culture of thinking beyond the problem and trying to understand how does the solution affect the person who we're developing this solution for. Traditionally, a lot of organizations have failed to draw a line between how individuals perceive their products versus how they react, because they think if there is a reaction and it appears to be positive, then everything is positive. So design thinking is actually becoming a differentiator, because you envisage how the people you're developing the solutions for will react. And therefore, as part of this process, you have to ask yourself a lot of questions around the solution beyond the solution to the problem. And in the next section of the presentation, I will be touching on that, including comparing the design thinking process to the actual AI or machine learning process. So the design thinking process has mainly 5 stages before you actually implement or put your process in production, where, as I said, you've got to conduct research to understand who your users are, how they react, and how the solution fits in your in the operating model. But it's also important that you define your research objectives clearly, including the secondary research objectives that might arise from the primary problem. In a lot of organizations, especially the design thinking driven, there has to be evidence of brainstorming or highlighting the opportunities to innovate, and not innovation for monetary value, but innovation to come up with better solutions, or innovation to actually solve the problem, especially where there are complexities. There has to be a bit of tactical representation of your best ideas, including ideas demonstrating that you understand the problem and how it fits into the lives, or it fits in the operating model when your solution is in use. and the testing part, which is normally underestimated, which has to be rigorous in which also includes the users, as well as assessing their feedback. Now, let's look at some of the examples where, or scenarios that design thinking is actually critical. And the first one is marketing. And I have to apologize. A lot of the use cases I'll use are maybe banking or insurance because of my background. I've always heard about people saying, I am going to, we've designed an algorithm to offer the right customer, to offer the right product to the right customer through the right channel. And normally it's based on just data. And it comes back to what Leo said, why we're always making assumptions about the data. And some of the considerations is to go beyond the problem and ask yourselves while designing these algorithms, what are your customers expecting? How do they perceive your solution? How do they perceive the value of your solution? What have they complained about? And this is why in some company in America, you've got the American Customer Satisfaction Index, which measures how customers feel about products as opposed to the traditional take-up, the traditional regression models that predict a customer will take up a product or not take up a product. So in that setting, you have to go beyond what you have in your data. Customers took the product or they did not take the product, and engage with your customers as part of your design process before you start using your solution, whether you've demonstrated, do you know the customer? Do they feel respected? Do they feel protected? Do they understand that you're showing them there's an element of trust? The data points for measuring these attributes are very different to the data points that you already have that are telling you the customer took the product or they did not. And if you do not, we do not have that data as part of testing and prototyping your solution, make sure you do collect them. And there's lots of similar use cases, especially around customer value management in the retails, places where assumptions are made around data that the customer has a product, so it means they're happy with them. Imbalanced classes or the problem of data imbalance is a very big one across all industries. A data set is said to be imbalanced if one of the classes has many more observations or records than the other. Just a few examples where we've seen imbalanced data sets, like in fraud, where you've got less than a percentage of transactions are fraudulent, the banking space. When you test people for a disease, including what we've seen in the pandemic, normally the ones with the disease constitute a very small proportion. Emails predicting failures in equipment, looking at people who reacted on a website by clicking a certain product, or even intrusion. A lot of algorithms or traditional machine learning algorithms have been designed with the assumption that there will be a balanced data set or balanced outcomes in what is being measured. And it's important that you have to look at the problem and understand the role or the source of imbalanced data set, and you need a bit of design element to understand this. So the first thing is you need to ascertain whether the imbalance is intrinsic or extrinsic. Intrinsic means the imbalance is part of the problem. So it is the way it is. For example, if you've got 0.01% of transactions are fraudulent, that's how the problem is. And in my experience, I've seen people say, no, we don't have enough data. You're not going to ever have enough data. Extrinsic means there's some external factors that's affecting the quality of the data. And you either have to fix whether it's a quality of data, the way data is captured, or sometimes it might be a data quality issues related from the way things have changed. And it's important to be able to explain. So there's some sort of external factor affecting the data. It's important that as a data scientist or practitioner, you think about this problem and solve it upfront, or identify the source of imbalance or the type of imbalance upfront. Then check whether the imbalance is between the classes or within the classes. That's also very, very important. And one of the areas we see this is in image data in the medical field, mammography data, where there's a big imbalance between, even within the minority class of people who have cancer in hospitals. And here is an example where you'll see that the localization of the data is actually very, within the class is very different. I mean, there's an imbalance within the minority class, because if you don't ascertain this early, you're likely to end up having a problem where your model generalizes very well with the majority class and you think that it's working, but actually it fails to correctly predict the minority class. And the same thing applies for traditional quantitative outcomes, so regression types of outcomes. On the right there, you'll see where you've got two samples, and the smaller sample has multiple distributions within itself. The other part of the imbalance that must also be investigated as part of understanding the nature of the imbalance is where you've got an overlap. And sometimes it's even complex. And I want to give you an example. In the financial sector, we've got various types of criminality that happens on our customers' accounts. And criminals change their approaches very, very frequently. And sometimes you'll have data quality issues where the people who capture these records don't capture it accurately. You end up having fraud cases that are captured as non-fraudulent, or non-fraudulent cases are not captured correctly. And you end up in overlap. So you might have behavioral differentiation, but it's still a problem, because if you've got a few fraud cases that are being represented as non-fraudulent, you end up in a situation where your models are not able to learn properly. But you might also have scenarios where the problem is so complex that there is no behavioral differentiation between drivers of the outcome. So think about cybercrime, where we've got what are called AI-enabled cyber attacks. And criminals train these systems to be able to mimic the exact behavior of legitimate users of the system. So behaviorally, you're not able to differentiate, and it's not because your models don't work, but you've got a situation where you need to rely a bit on expert information to be able to ascertain that you've got an imbalance, but also you've got an overlap that cannot be predicted. And therefore, you want to correct for the imbalance before your algorithms can become significantly useful, or else you're going to have a situation where you generalize well on the majority class and you fail to predict the minority class correctly. I want to focus more on the sampling methods. The cost-sensitive methods depend on the sampling methods, but also depend on almost a strategic way of prioritizing, what is the cost of misclassification from either side. But quickly, traditionally, and this is common, especially in credit scoring and other areas where people undersample the majority class, and it's worked very well, but you reduce the dimensionality of the majority class, and the stochastic distribution created there is actually very different from reality. So you do expect that your algorithms are not going to correctly predict some of the cases that were not part of the training data set. Some areas, people, especially where there is very few observations in the minority class, like fraud, they decide to oversample the minority class and create new data points within the same data space of the minority class. But also here, what's happening, you're creating a lot of noise. So it also works, especially in very big data sets, but you create a lot of noise and duplicating cases because you're duplicating cases and creating a distribution that did not exist of the minority class. It also leads to a lot of misclassification, especially if things change and you have new cases that were not very similar to what you trained your data sets on. What has worked very well, and it's demonstrated success, is synthetic minority oversampling. And this is where through the synthetic or the smart algorithm, you do oversample a minority class by creating new cases using the K nearest neighbor approach. And therefore you generate new use cases, not similar in the same data space, but between data points of the minority class. The beautiful thing about it, that it allows you to filter any duplications or similar cases that might create noise in your data set. And therefore you end up correcting for noise that might lead to redundancy or even overfitting of your models, especially when you're training models and they give you so much confidence because of synthetic data. When you're applying them to real data, they do fail. I just want to go through an example here, which was actually done by Abhay Pada from Amazon. So we've used these approaches because of confidentiality. I could not use our organization data, but he's done the exact thing. And there's two things I want to bring out here, where he tests two different types of algorithms, but also he solves for the imbalance using synthetic minority oversampling. And in this case, he's looking at, he looked at a German credit data set. In this data set, there's only 0.172% of transactions that are fraudulent. Obviously, you can tell that that is an imbalance. And so he has to train an algorithm that will classify most of the fraudulent transactions correctly as fraudulent and classify correct legitimate transactions correctly. What you see here is part of his output. When you look at the bottom left there, we look at his classification matrix. It's actually not that bad, but it can get worse, especially if you've got even a bigger imbalance. Again, when you look at the right, I just need to point out, I'm not a fan of the ROC curve, and the main reason for that is that because you've got because the majority class has got a very big proportion of the cases in your data set, you could end up having a scenario where you're being misled that the overall accuracy is high, when actually most of it is coming from the majority class. When he applied the same approach to the random forest, you can see the number of false positives reduces. And let me just go back again and point this out. What you see here is the false positives. So these are what have been misclassified as fraudulent when using the logistic regression. But what you have here is the random forest. You can see over 80% of the false positives, actually 90% of the false positives, have been filtered out using the random forest. So it's a big lesson, and it's very similar to Leo Breman's case, where certain algorithms just don't work well, and maybe as AI and machine learning practitioners, we need to adopt an algorithmic culture where we look for the best algorithm other than make assumptions. But also one of the things he mentioned, which I think I can relate to this use case, is that some problems are just complex and require complex solutions or a complex approach, depending on how you view it. But also, how do you measure these things then? Sometimes, because in a situation where you've got an imbalanced data set, measures of goodness of fit might not be the most sufficient ones. You might have to resort to operational measures from the confusion matrix. And I think this is a very standard slide. I don't want to spend time on it. And beyond what you see there, you have measures like the harmonic classification, the sensitivity, the false negative rate. But there are other measures like, for example, the positivity predicted value. What is the likelihood that it's actually positive when it's predicted positive? I'm also not going to spend a lot of time on this. So while the goodness of fit measures will give you a measure of how good your model is in relation to others, it might not give you it might not give you robust measures of how your algorithms will work in an operational environment. And therefore, measures like this will be much more preferred compared to the traditional measures. So these were for a binary scenario. For a multinomial scenario, you just have to apply, extend the same measures to this scenario. The problem of data is not just limited to discrete data. I'm not an expert in generative adversarial networks, but a lot of research has shown that much of the challenges we're having around use cases related to image data and classification arise from the inability to generate new data to solve for biases or imbalances. A lot of image data was not taken for analysis, so you'll find that it requires cleaning. Some of it is old data, especially medical data. And generative adversarial networks through an adversarial setting allow you to generate images with parameter setting that would help you solve for representation or even solve for quality problems. And when thinking about using this data for classification, and like, for example, the beauty contest one, someone would have thought about representation and corrected for that. The reality is we need these algorithms in one way or the other. This is just an explanation of how advanced these techniques have come. And therefore, solving for data representation is not actually a challenge anymore in some areas. These images are not images of real human beings. They have just been generated using deep learning neural networks. But we have cases where there have been challenges in collecting data, maybe because of budget or costs, or even there's certain scenarios where during the collection of data, it was not easy to get to the participants. And therefore, if you're to make assumptions about your population using that sample, you'll end up with estimates, or even you're likely to reject or accept hypotheses of what you're trying to measure very, very easily. So bootstrapping is also another approach which can allow you to make or come up with better estimates, or even make much more robust conclusions, where you draw samples from the data you have, and the distribution from the bootstrap of samples can be used to obtain much more robust estimates, or even make much more realistic assumptions about the population. The other part could be introducing polynomial outcomes in your models to cater for nonlinearity, and you could have polynomial variables to any order, especially where you're dealing with variables that have a very strong linear relationship with the outcome. And this is an example of a propensity model we built at the bank in 2014, where we increased the take-up rate by 700% by just introducing polynomial variables in the model. And it worked very well because it allowed us to align the profile of a customer to them likely to take a product on a particular day. I want to touch a bit on generalized linear models, especially because it's also a key area where I've seen a lot of problems in inability of models to predict correctly. Now, traditionally, we all start regression with a traditional linear regression. And the objective is, as usual, to predict a certain outcome with the help of various predictors. But normally, the assumptions of what you're predicting are normally distributed, or the errors of those variables are normally distributed. But what happens is, in real life, ask yourself, how many outcomes or even scenarios are normally distributed? Very, very, very few. You know, this is an example of income. On the right there is the number of it's a take up of a certain product in the bank. And if you're to approach it traditionally like that, you'll end up in a situation where the stochastic distribution or the outcomes or the predictions from the normal distribution will be very different to what you observe in real life. And the difference is actually what you miss out on or what you misclassify. So general linear models allow you to tailor the variables or the response variables to the outcome of the distribution. Sometimes it might be the normal distribution, but without general distribution, think about loss models in insurance. And I think that type of thinking should all apply to a lot of use cases, other than make assumption that everything is likely to be normally distributed. I want to jump quickly to a different scenario. We've been going through vaccination, and we've seen that there's a proportion of the population that is very willing to be vaccinated, which is a good thing. There's another proportion that is undecided about vaccination. And then there's one that is totally anti-vaccine for various reasons, and people are justified to, people are allowed to have, to live by their opinion. We've got the same scenarios in, marketing. How do people feel about it? I've seen a lot of that. One of the key studies I did when I was doing my studies was to understand what are the attributes that make someone become a victim of fraud. On the right there, you'll see percentage utilization of products. So in scenarios like this, what normally happens, people drop one of the classes that is gray. So they're undecided, for example. But if you think about it practically, maybe that is a class you should be focusing on. Because if someone has decided that they don't want to be vaccinated, you can't do anything. But if someone is undecided, you want to find the factors that make them undecided, or maybe educate them so that they can make the right decision. Because if someone is undecided, it means there's an opportunity to change their mind. And therefore, instead of changing a multinomial problem to binary, and I've seen a lot of people do this, you need to use the right algorithm that gives you a multinomial outcome without changing the representation of the problem, because the factors that drive someone to being unsure of something are very different to someone to the factors that drive people who are either positive towards something or negative towards something. And when we did this study, we actually found that there were significant factors. For example, we included all this information to collect those factors as part of the survey. And there were differentiating factors that were statistically significant between those who were not sure about something versus those who were totally against it or were for it. So for example, we had customers who believed it was a responsibility of the bank, to look to secure their transacting channels. It was all the responsibility of the merchants, or maybe only people who are not careful fall victim to fraud. And because now that helped us to drive a more targeted, educational program on things that would help people who are unsure to even be more vigilant. The other area where we need to think about is behavioral outcomes. We've been living at a time where we make predictions and depend on predictions to take decisions or implement strategies. But we are in a situation where we need to influence outcomes other than take actions on outcomes. And so think about, I want to give you an example. When you go apply for credit today, or in most cases, they will tell you you qualify for credit or you don't qualify. So someone has taken a few attributes and put in a model, and the model says, no, you're good for credit or you're bad for credit. But we're at a time where we need to influence the outcome. So think about this. Instead of someone accepting or rejecting your application, how about they work with you and drive certain behaviors so that you can be a good customer? And that's why reinforcement learning is becoming a very, very powerful approach, and maybe even with other behavioral approaches of machine learning. And with behavioral approaches, a customer is looked at as an agent, or individual is looked at an agent placed in an environment, and their actions are influenced so that the outcome or the future outcome can be desirable. This is actually becoming prominent in credit scoring. And also think about financial inclusion. We have a lot of cases where people don't have historical data. For you to drive that, you need to drive behavioral ways of influencing an outcome, so that people can be rewarded for behaving in a certain way so that you can actually minimize the risk. And don't get me wrong, people work with whatever they prefer. It's just that you're achieving the same outcome, risk management, but the other one, you're influencing the outcome as opposed to using an outcome to make a strategic decision. Movenbank is a very, very good example of that. Movenbank drives behavioral outcome by, first of all, predicting your needs. Are you a customer who invests to go on a holiday, or do you invest to go to build a house, or do you invest to maybe to pay for school fees for your children? What they did was to use a behavioral approach to allow you to save, and so that you can fulfill your objectives. But what made it nice for their customers is that they made sure that they inform you that we already know why you're saving. So that behavioral setting helps build on trust, but also builds on relevance, because you don't want to be receiving things that are not in line with what you want going forward. When they did this, over 40% of their customers took their savings and investment products because they felt that behavioral setting was more aligned and personalized. Let me just check the time. We'll try to finish in the next 5 minutes. So we've also, Yes. So we design a lot of algorithms and processes to reimagine processes. And to give you an example of a process is, I want to talk a bit about the Apollo program. In the 60s and 70s, through the Apollo program, the Saturn V was designed to lift scientists to the moon for research purposes. And what you see on the left there was, the rocket, the Apollo 10 rocket. And a few years later, they made a bit of cosmetic improvements to that rocket and ended up to the 5th version later called the Apollo 15. Elon Musk comes a few years later and decides, no, I'm going to have to break down this whole problem and start from scratch. And he designs the SpaceX. It cost the Apollo program $1.2 billion of today's value. It cost Elon Musk, what you see on the right there, less than 5% of that. The two thought processes are both allowed, and it also extends to the types of algorithms where you change the problem and you still execute the same outcome. On the left, there was a bit of incremental thinking. On the right, you've got a scenario where someone broke down the whole problem, and that whole process of breaking down the whole problem and restarting is what we call first principle thinking. What we see in the market is we take the old problem and apply the algorithm to the old problem instead of changing it. But it's short-lived. For example, credit risk 10 years ago is not the same as credit risk today. Fraud, marketing, some of the diseases that exist today are not the same, or some of them mutate, and you need to always come up with a totally new way of solving the same problem. I'm going to rush a bit to finish. A few years ago, we implemented a system called Manila to help reimagine our forensic processes. How did we do that? In an iterative environment, we could have just built rules and algorithms in each stage of the forensic process. What you see on the right is us reimagining the whole process, saying, listen, I think we can break down, this is where the algorithms can do this, what the algorithm cannot do. So sometimes the algorithm can have much more impact in a process if the whole process is reimagined, other than incrementally, almost digitizing an existing process. So taking an old process and putting new solutions on it, which does not necessarily realize the potential of what data could do. The last scenario is, what if you don't know what you don't know? The prototyping stage of the design thinking process can help you get feedback that something is likely to be wrong, especially if you're starting something new, investigating a problem where you've never collected data on. And this was evident when Facebook actually went to a partnership with a company called Admiral. So Admiral wanted to use some of the Facebook data to actually calculate premiums. While the algorithms were 100%, but Facebook had controls in place to ensure that this customer data is not used from a privacy and ethical perspective. Without that control in place here, it will have led to a much bigger problem. And so I want to conclude the next two slides by convincing you that while design thinking has been used for fashion and digitization, it has a major role in how we design solutions in the AI and machine learning space. In fact, in places like Menlo, it's presented as a cost because they think it humanizes the data science process. And you can see similarities there from when you define your hypothesis, because at that time you're supposed to empathize and think about the customers or the human aspect of the problem. You gather data, you also need to think about the outcomes and the decisions of your data just beyond the data and the problem. Up to when you evaluate and prototype your solutions, you need to humanize that process. Because the science alone is proving not complete, but also the science is taking away trust from machines. Everyone keeps talking about digital transformation, but we have things like customer centricity, we have disruption. Only through design thinking process, we are going to realize the total economic value of data. So instead of creating incremental improvements, some of the challenges require us to think and design solutions that can solve some of the problems we're seeing. For us, I mean, practitioners, we are enabling the change of business models because things are changing. The ways of working are changing. Data and AI are, driving disruption into different business models. And if that is not replicated by creativity around data and algorithms, we're likely to have a lot of solutions created that are much redundant than solving what is supposed to, or solving the problems the way they're supposed to. And therefore, I want to finish by pointing out design thinking humanizes the AI and machine learning process. I've spent a lot of time talking about scenarios where I think due to a lack of design thinking, things could have been done much better. But also we need to introduce a human-centered approach to innovation around the use of data so that we can use AI to bring people and have all the possibilities of technologies, fulfill all types of strategies or objectives we want data to play a role in. Thank you so much, and apologies I went a bit over time.
Thank you very much, Mark. It was really an exciting talk, and it's really useful and super informative to see the challenges of the adoption of machine learning and artificial intelligence from the side of the user. Yeah, and I think it was really an eye opener for many of us. I would just like now to ask Amira to guide us through the questions. And I see we have 2 questions in the Q&A. And Amira, I think we can allow Kanshu to talk and to ask his question in person, if you don't mind.
Perfect, yeah, sure, go for it, Kanshu.
Thanks, Amira. Can you hear me?
Yes.
Cool. Thanks, Amira. Thanks, Francesca. And thanks, Mark, for that interesting talk. So, design thinking is one way to look at, I guess, a problem. What are the other methods that are typically in use that one could use other than design thinking?
So, as I said, design thinking is a mindset of driving how you look at a problem. But in a more cultural perspective, almost design thinking complements your expert knowledge in a certain field. In my view, I don't think design thinking is an alternative to other methods. Design thinking complements your approach to the way you use your existing skills to solving the problems. It's basically, in my view, it's an extension of what competencies you already have to increase your chances of success while solving the existing problems. I do think when you look at the differences, as I said, the examples I mentioned earlier, all organizations are investing, they have money. So the money is not a differentiator. All organizations have data scientists today, but design thinking allows them to view the problem in a very realistic way so that the problem can be solved the way it's expected to be solved.
Great. And I guess my second question is, do you know much about systems thinking and what the difference might be between design thinking and systems thinking?
So systems thinking and design thinking is almost the same way, but systems thinking is design thinking focused more on systems and how systems integrate to the solutions that are being designed. But it's basically a design thinking for systems thinking.
Great, thank you so much.
Yeah.
Perfect, thanks. Thanks, Kanchu. And maybe I can also thank Mark again for the talk. And I have also one quick question since, yes, I don't see any more questions in the Q&A, but if anyone has, please post it. But Mark, I was just wondering, like, you know, you explained very nicely when things can go wrong, how we can think about getting our data better distributed and this whole process of making things okay. But who should even own this process in the first place? Like, especially in an organization, you know, where you have, it's very often siloed, where you have people designing the algorithm, people handling the data, people using the algorithm. But should there be one sort of central entity that controls this process end to end, like to make sure these problems don't happen?
Yeah, so Amira, that's a very good question. I think if, for example, data and technology is your business, then it's everyone's business. When I'm talking about design thinking and data, it's about creativity and minimizing things going wrong, but also optimizing opportunities. And the first, it's a leadership thing, because leaders help people drive certain culture. Being data-driven or AI-driven is actually a culture. So it should be an accountability driven by leaders, because through leaders, people can drive a certain culture, whether it's, you know, I mean, I know organizations apparently like Apple, they do have design thinking sessions, and you have to demonstrate that evidence that you went through the design thinking process to demonstrate that, you know, you've gone through a process that is likely to result to success other than just a process. So in my view, it's a leadership, but it's everyone's accountability. We're going to go to a time where design thinking will be a competence, complementing your technical competence.
Okay, perfect. And then we have two more questions that came through, so maybe I can shoot them off quickly. So
sorry, I gave
yes?
the rights to speak to Victor and Bruce, so you can invite them to ask their question in person if you want.
Okay, sure. Maybe Bruce can go first, since it's a follow-up from what was just said. So Bruce, if you want to unmute yourself.
Thanks very much indeed. A very nice talk, by the way. So just a very quick add-on to Amira's question. The notion of designing the algorithm, I'm curious whether you think that we should be worried about the fact that there perhaps is no longer even a designer of the algorithm, and things have moved on to some kind of design autonomy, if you will.
That's a very great point, actually. I think the implications or outcome of an algorithm should not just lie with the designer, should lie with everyone in the value chain. The way I designed the talk was so that, you know, the role of algorithms and data is not just left to the data scientists. It should be questioned by everyone in the value chain. Because if things go wrong, an organization is not going to pinpoint to, you know, it's not going to solve anything by saying, you know, the person who designed the algorithms here. So at the requirements stage or the problem understanding, we need to make sure that the human aspect of the problem is questioned and understood as part of the problem. So it should be a tradition that is inclusive of everyone.
Great, thanks, Mark. And then maybe the final question can come from Victor. And before you unmute Victor, I just want to say to Mark that there's lots of compliments in the chat. So Paul also even says that the talk was absolutely fantastic. He wishes it was longer, and a lot of thanks. So yeah, Victor, you can go ahead.
Victor?
We don't hear you.
Maybe there is a problem. And I'm sorry.
Maybe he can type the question.
Yes, I have it here. Okay, I will just read it out to you. So Victor says, maybe I didn't hear how innovation is driven from engineering to design is related for proper understanding and appreciation. Could you briefly explain how design thinking has impacted engineering?
So when you think of systems and technologies, traditionally technologies have come together and learned about how these technologies will work together and change the future. So, for example, I'm trying to think of marketing. I think marketing will be a better example. And they've designed it because there was a certain need for a customer, for example, needed a certain, they knew a customer would take a product. So they engineered processes so that a customer can get access to a product. But traditionally, engineering was around making things happen. So data will be used to understand linkages and behaviors so that something can happen. But what we never thought about was, how do people perceive that experience? What does it mean for them? Those questions were not asked. In fact, data around those questions were totally not asked. And people had to accept what was offered to them, right? They had to work with what you have. Like, listen, there's very few banks, or there's very few flights going to New York. So you got to work with what you have. So your comfort was built around that. And with this digitization era where everything is globalized, how people perceive what you're giving to them actually matters. So it ends up becoming more about the experience other than the product itself, because in the platform world, I mean, you can just use your application on the phone now to get anything from any other company. I think maybe that's an example that can allow you to think about, to differentiate between just engineering a process so that it can work, but also it differentiates it from a design where you sit down and ask yourselves, how will the customer think about this? What are some of the roadblocks of the blocks that do they go through on a day-to-day process before you know, they use the product, or before they use a certain process? So there are questions, actually, these are more of design questions beyond what you're offering. And apologies about my banking example, sorry.
No problem, Mark. Thank you so much. On the contrary, it's really interesting, as I said before, to see, to get this kind of feedback from the actual user of all the artificial intelligence setups, yeah, and to learn about the challenges and the opportunities to fix the systems. Yeah. That was really very nice.
Yeah, the Facebook Cambridge Analytica. I don't like using negative examples in sessions, but the Facebook Cambridge Analytica, there was a process engineered to collect data, and that data was engineered to, you know, to drive users to make certain decisions.
Yeah.
A design thinking approach would ask, but what does this mean for the user? Will they be okay with it? Maybe can we talk to a few of them and understand if they're comfortable with this approach?
Yeah.
Or, you know, so we place ourselves in the shoes of the human being and measure human experience beyond just the process that has been engineered together.
Yeah. Yeah. And I think these are fantastic words to conclude the session, Mark. Thank you. Thank you so much. And Mark agreed to have another 10-15 minutes for us, if you would like to join him and have a chat with him in a more informal virtual setup on the link that I just shared again in the chat. So if you would like to interact with Mark just now, please join us on the next link. So Mark, thank you very much again for being with us this evening. It was really, really very interesting, and you heard or read all the positive feedback in the chat. So thank you very much from all of us. Amira, thank you for being with us and moderating the questions. And Ilya, thank you very much as usual for the technical support. So thank you very much, everyone. Have a good evening, and I hope to see some of you in our social virtual space. Thank you very much. Have a good evening.
Thank you so much.
Bye. Bye. Thank you.